Okay, next example. Because I should read it as I'm writing it, because I'm sure it's not very clear. Okay, so we have cosine alpha over 1 minus sine alpha equals 1 plus sine alpha over cosine alpha. We want to try and make one side look like the other side so we can verify that it really is an identity. Okay, this is a harder one where we're actually going to use a conjugate to see if that helps do anything. The reason I think to even use a conjugate is I've got this 1 minus sine alpha. So if I multiply by a conjugate, like 1 plus sine alpha, it will end up giving me a sine squared. And if I have a sine squared, then it might match a Pythagorean identity that I could then possibly use to simplify the problem. So that's why we would even think about doing something like that. Okay, so we have cosine alpha. We're going to leave there, and we're going to multiply by the conjugate, 1 plus sine alpha. So on the bottom we have 1 minus sine alpha, and we're going to multiply by 1 plus sine alpha. So it's fine for us to multiply these into the problem because this over this equals 1. So we're multiplying by 1, we're not changing the value of that side at all. Okay, let's go ahead and distribute the cosine through. So we're going to have cosine alpha, because cosine alpha times 1 is cosine alpha, plus cosine alpha sine alpha. And then let's go ahead and FOIL the denominator there. So the denominator will be 1. And then I'll have a positive sine alpha and a negative sine alpha for my outside-inside term. So those will cancel out, so I'm not even going to bother writing that. Is that okay? I hope. And then I'll have negative sine alpha times positive sine alpha is negative sine squared alpha. Okay. Now this thing is the Pythagorean identity if we solve it for cosine squared. I'll show you that in just a second. I think that'll be helpful. Okay, so for now, just if you don't know what I'm talking about, just believe me, this is going to be cosine squared because of our Pythagorean identity. So that gives us cosine alpha plus cosine alpha sine alpha over cosine squared alpha. Okay, so now notice how we have a cosine here that can go away with one of these, because cosine squared alpha is like cosine alpha times cosine alpha, right? So we can rewrite it that way. So that can reduce with that, and so can that. But we're still left with 1 cosine alpha down here. And of course this turns into a 1 when we reduce it that way. So this cosine reduced with that cosine is 1. And this cosine reduced with that cosine is also 1, but we don't need to write that part. So we have 1 plus sine alpha. And we still have 1 cosine alpha remaining on the bottom that we didn't reduce with the other ones. Okay, now look at our original problem. Look what happened. Without even trying, we ended up getting the other side of the problem. Now I was going to show you the Pythagorean identity really fast, in case you'd forgotten. The Pythagorean identity says sine squared alpha plus cosine squared alpha equals 1. So cosine squared alpha would equal 1 minus sine squared alpha. So that's the thing we just used. Now some of you might be thinking, oh, but I moved the sign to the other side. I moved it across the equal sign. Well, that's okay if the if the identity's already been established like this one has. We already know that this one's true. And so when we know an identity is true, then that's legal. But when we're trying to prove that an identity is true, then we can't do that. That's when that rule can't be done. So that's the substitution that was made in the problem to be able to make it work. Okay, there we go.